Good afternoon, everyone. Welcome to this lecture on drought monitoring case studies in Africa. So I will share my screen and I will start the lecture. Okay, so just a very short introduction about my background and why I'm giving this lecture. So I'm a senior research scientist at the Technical University of Vienna and the team lead on the soil moisture applications group. My background is in earth sciences, mainly physical geography and hydrology, which I studied in the Netherlands at the TU University. And as part of this, I was also participating in the calibration validation campaign of the soil moisture ocean salinity satellite of ESA. I then did my PhD in remote sensing at the Technical University of Vienna, so where I still am now, in the hydrology group and the remote sensing group with Professor Wolfgang Wagner, who you know from the last lecture, mainly working on retrieving vegetation and soil moisture information from active microwave observations. I also planned and installed an in-situ soil moisture network for the validation of satellites. Recently, I've been working on my ESA Living Planet Fellowship, which was looking at the impact of drought on vegetation dynamics with Sentinel-1, and also on several World Bank and Austrian Development Agency projects on drought indices and enhancing drought early warning, particularly over Africa. So just to see where we are in the series of the lectures. So the last time you had some lectures on global flood monitoring and surface soil moisture anomalies. And today we're going to look into drought monitoring case studies in Africa. So just to go back to what you might have seen in the last lecture. So this lecture was on flood monitoring and anomalies. And this slide is from that lecture where you could see what Professor Wagner showed you, let's say these anomalies in soil moisture based on HSAP ASCOT surface soil moisture data record, where in blue colors you can see wetter than usual conditions and in red colors you can see the drier than usual conditions. And also what he mentioned was that relating these anomalies to actual floods and droughts is not as straightforward as one might think. And this is what we're going to talk about today. So we're really going to look at the choice of soil moisture data set to use. How can you calculate these baselines or these normals, climate normals and anomalies? Also, how can we calculate the drought indicators? What different indicators are out there and what should you consider if you use them? And we'll finish up with a case study in Senegal, where we'll look into drought indicators, but also look into using surface soil moisture from satellite data for early season yield predictions. So to start with a quick overview of drought, which many of you might already know, but if not, then here we just go through it shortly. So a drought usually starts with a meteorological drought, which means that we have precipitation deficiency or high temperatures and increased evapotranspiration. If this continues, then we can go into an agricultural drought where we have a soil water deficiency, which leads also to plant water stress. This can then develop into a hydrological drought, which reduces stream flows and also reduces inflow to reservoirs. And this can then also lead to socioeconomic drought and famine, whereas, of course, also an agricultural drought can directly lead to socioeconomic drought and famine. So today we're specifically focusing on soil moisture. And why are we doing this? Because soil moisture basically gives us the plant available water. So of course it is the sum, let's say, of the precipitation minus whatever percolates into groundwater, what gets let's say what's evaporation and transpiration from the plants. And so actually soil moisture gives us a very direct measure or indication of what is available to plants and if there's a shortage for plants actually. And we use for this microwave remote sensing of soil moisture. So most soil moisture products are based on microwave remote sensing, as Professor Wagner has explained to you in the last lecture. And so with microwave remote sensing, we can measure the amount of water in the soil for the first few centimeters. So this is what you can see here. So like the first couple of centimeters, and the soil exists of solid particles, water and air, and the microwaves are sensitive, let's say, to the outbound water within the soil. And using algorithms, we can retrieve then the soil moisture from the microwave observations. Okay, but as I said before, it's very important to also choose a data set for measuring soil moisture, but particularly for doing drought monitoring that fits actually your needs and your application. And so there are a lot of different satellite missions that have been in space or are currently still in space, and this is an overview of that. So on the top here, we can see passive microwave missions, which provide surface soil moisture data. On the bottom, we have active microwave missions that provide surface soil moisture data. And as you can see, the first missions from passive microwave data started at the end of the 70s, actually. So there is quite a long data record available of surface soil moisture data, but it is based on a combination of different satellites. For the active missions, they are since 1991 available. Also, a combination of different satellites can be used to give you a long data record. The advantage of active microwave missions is that they have a higher spatial resolution. And this is also something that you need to consider for your application. So this is a table that gives an overview of a lot of surface soil moisture products that are available at this moment. And just to go through them shortly, what their different characteristics are. So the longest, let's say the data records going back the furthest in time are the ESA CCI soil moisture and the C3S surface soil moisture data sets. So they are the ones that are based on the first satellite at the end of that was launched at the end of the 70s. As you can see, their temporal resolution is 1 to 2 days or 10 days. And then the latency, so how fast do you get the data after the satellite has actually made its measurements, is that for the ESA CCI dataset, this is a year. For the C3S dataset, which is based on the ESA CCI dataset, this is 10 days. So if you're doing near real-time monitoring of droughts, let's say the C3S dataset, you need to wait for 10 days to get the data. The spatial sampling is, of course, also very important, and this is 1/4 degree for these two datasets. The advantages, they are both freely available. And then if you really need near real-time capabilities, so you really want to have the data as fast as possible, the HumanSat HSAT datasets, which also Professor Wagner was talking about in the last lecture, these data sets are available with a latency of a maximum of 1 day, and usually the data is available within a couple of hours. The spatial sampling of this data set is 6.25 or 12.5 kilometers. The only downside of this data set is that it only goes back until 2007. So it is a shorter data record than the ESA CCI data sets. From this HSAT surface soil moisture data set, there's also the so-called Copernicus Global Land Surface Soil Water Index. And this gives you information on root zone soil moisture as well. And this is available also since 2007 and with a latency of 3 days. So this can also be used actually quite well for, let's say, monitoring of droughts. Then there are the ESA NASA satellites, SMOS and SMAP, and they were launched respectively in 2010 and 2015. And they are also available in near real time, and they have a temporal resolution of 1 to 2 days and a spatial sampling of about 36 kilometers. And then if we look at high resolution data sets, so what we have is from SMAP, there's a high resolution, let's say root zone soil moisture data set. And then from Sentinel-1, there is a high resolution surface soil moisture data set available. So the SMAP data set is available at 9 kilometers. And the Sentinel-1 product is available at 500 meters, so half a kilometer basically. The disadvantage of all these data sets is that they are available since 2015. And I will tell you why this is a bit challenging in drought monitoring later on in this lecture. And the last data set that I would like to mention is the Wandersat, or Planet Now data set. And this is available at 100 meters, but this one is not freely available. The spatial coverage is only available upon request. So you need to pay for this, and then you can get data over your area. To give you an idea of what these data sets look like, so what we're looking at here is the surface soil moisture from Sentinel-1 data over Italy for June 2020. June 2020 in Italy were relatively normal conditions. So let's say precipitation temperatures were very normal. So also soil moisture was relatively average. You can see here this very high spatial resolution, right? Because this is just a part of Italy. And this is data at a 500 meter sampling. And then if we compare June 2020, which was a normal year, to June 2022, which was the drought, let's say, especially the north of Italy suffered from a severe drought, then we can see, let's say, these anomalies in the soil moisture, where we can see that soil moisture is much lower than it was for a normal year. So you can see here that soil moisture, especially in the Po Valley, is around 10 to 20%. So yeah, these are definitely drought conditions. But what we can also use, so this is an example for the Copernicus Global Land Surface, the soil water index. So the challenge with using 500 meter data is, first of all, that you need to do the processing for this, which is, let's say, computationally very expensive. So if you want to look at larger regions, you can also use a coarser resolution data set. So this is an example of the soil water index anomaly for March 2023. So I processed this last week because this data is available in near real time as well. And so these are, let's say, the anomalies for March, where we can see indeed the drought in Tanzania and Kenya and in Namibia as well. Okay, so one thing to consider, let's say, in soil moisture data sets is like, what kind of spatial resolution do you need? Do you want to look very much in detail, or do you want to look like at full continents? Because if you look at the full continent, you're not going to need data at 500 meter resolution. Whereas if you really want to look specifically into a certain area or a catchment, then of course 500 meter resolution data is very useful. The challenge, however, with the high resolution data sets are that they are only available since 2015. So calculating deviations from the long-term mean are more difficult, which we will discuss also later on. But the first thing also is that it doesn't only depend on the spatial resolution, the temporal resolution, and let's say the length of the time series. What's also important is that you know what is the quality of the data sets and what are, let's say, the strengths and weaknesses, and especially like how do they relate to the region where I'm looking at and also my application. So validation of the satellite soil moisture products before you use them, I think, is very important. And we can look, like usually if we do a validation of satellite soil moisture products, we look at two different statistical metrics. So the first is that we look at absolute deviations through the bias and the root mean square difference. So this is basically showing us how much is our satellite measurement deviating from our reference measurement in absolute values. The other one is the statistical dependency, which basically shows us like how do the two data sets vary in time. So if I have, for example, low soil moisture in my satellite data set, do I also have this in my reference data set? And as reference data sets, what can usually be used are either in situ soil moisture measurements, so really like having sensors on the ground that measure soil moisture over a long period of time, We can use model data sets as reference data, or we can also use other remote sensing data sets as reference data. Now, it needs to be noted here in terms of validation of satellite soil moisture that the reference data set is not necessarily the true soil moisture. So an in situ measurement, for example, is a measurement that is representative for, let's say, a couple of centimeters of volume of the soil, whereas, of course, our satellite measures a pixel of at least 500 by 500 meters, right? And even if you have the very coarse resolution satellites, they even go into tens of kilometers. So let's say your in situ measurement is representative for a very small area, whereas your satellite gives you a much bigger footprint. So if, for example, your in situ station is installed in a forest, but within your satellite footprint, you have much more agricultural areas, then it can already be that you have a difference between your in situ measurement and your satellite measurement. The same for models. Models also, they are driven by the input data. So this also, the quality of models depends very much on, let's say, the quality of the input data. And other remote sensing data sets, like, for example, comparing ASCOT data to SMOS or SNAP data, of course, also the other satellite soil moisture data sets have their strengths and weaknesses and are also not, let's say, the true soil moisture. But if we compare all these different data sets to each other, we can get a good indication of where certain soil moisture products work well and where certain soil moisture products don't work so well. So if we look at this, this is an example for Mozambique. So here we're looking at the root mean squared difference. So the absolute deviation between two data sets. And what we're looking at here is that we compared 4 different satellite soil moisture data sets. So the CCI data set, which was this very long-term record, then the HSOF data set, the one that's available in near real time, the SMOS data set, soil moisture, that's the one from ESA that was launched in 2010, and also AMSR2, which is another satellite. And they're all compared to GeoDust NOAA, which is a model which provides soil moisture data as well. And here we can see in which regions the retrievals perform better or perform worse. And what we can see is actually that we see the highest deviations between the reference data set and the satellites here in the center, basically, of Mozambique. And the pattern is relatively similar for most of the products, actually, except for SMOS and AMSR, they show a little bit higher deviations in the north. If we compare this, let's say quantitatively as well, we can see that the CCI data set and the HSOF ASCOT data set and the C3S data set show actually the lowest root mean square deviation. So let's say these data sets are the closest to the reference data set. So the lower this number is, let's say, the more accurate your soil moisture product is to, like, compared to the reference. We can also look at the temporal correlation. So how do the data sets vary in time, and does this correspond to each other? So we're looking here at the Pearson correlation coefficient. Again, we're looking for the C3S data set, the HSOF data set, the SMOS data set, and the AMSR2 data set. And here it means that if we have a high value, it means that they correlate strongly to each other. So anything where it's dark blue means that the product is performing well. And again, what we can see is that here in the center, we have some lower correlations, which we can see in C3S, but also we can see this a bit in the HSOF data set. And then for the SMOS data set and the AMSR2 data set, we actually see lower correlation coefficients and even correlations that are close to 0. So this means that, let's say, if for the one data set, the soil moisture is going up or down, the other one is not showing the same temporal variability, basically. And this is also seen if we look at this for the whole country. So again, a box plot for the statistics for the whole country, and we can see that the highest correlations are found, let's say, for the CCI data set and the C3S data set and the HSOF data set, and that is much lower for AMSR2 and for SMOS. So knowing this, you can already get an idea of which of the data sets are the best to use. So in this case, for Mozambique, this would be the HSUF data set or the ESA, CCI, or C3S data sets, if we compare it to model data, of course. Another thing that we can do is also look at in which months is our data set the most reliable, or are there periods in time where it's less reliable. And this is, of course, especially important if you're looking at agricultural droughts. You want to have a very accurate estimate of soil moisture, especially, of course, in the during the growing season. So when the crops are actually growing. And this is what we see here. So here we see the correlation coefficient per month, and we can actually see that in all months, correlations are quite high, except for the period July, August, September. Here we can see also negative correlations. For Mozambique, this period is actually the end of the dry season. So we can see that during this period, we don't have a very good soil moisture retrieval in all regions. But during the cropping season, which runs from October until May, we do have very good correlations. So there we capture soil moisture. Let's say there the satellite captures soil moisture really well. And this is something that Wolfgang Wagner also showed you last lecture, that one of the things that can happen in satellite soil moisture data sets is that we have subsurface scattering, that if it's very dry, that actually the signal penetrates much deeper into the surface. And that then we get this higher soil moisture, even though it's very dry. So what we're seeing here on the x-axis in the scatter plot is the soil moisture from the model, and on the y-axis we can see the backscatter from the satellite. And what we see is that there's this inflection point where if we have extremely low soil moisture, actually the backscatter is going up again. So then the model, let's say, the model retrieves high soil moisture, even though actually it's only because the signal penetrates deeper into the soil. So it's important to consider in all the satellite data sets, like what is my application, in which area am I going to use it, and to have a look at like where is the retrieval accurate and where isn't the retrieval accurate. And it's also important to really look at let's say the flags, the quality flags that are provided by in the product, so by the providers of the data, and to also apply these really to the soil moisture data. If you want to do a quality assessment of soil moisture before you start using it, I can recommend you to go to the Quality Assurance for Soil Moisture website. So the link is here on the left. And here you can do, let's say, the analysis that I just showed you. You can do this for basically all the products that are available. So you don't have to do this all yourself. You can just give in, like you can just tell this on this website, like I want to combine this product with this product and show me, like for this area, how well it's working. Okay, so now to the next section. So going to baselines and anomalies using satellite soil moisture data. How can we calculate baselines and anomalies, as this is not as straightforward as you would think? So there is a guideline from the World Meteorological Organization available to calculate climate normals, but this is actually for surface meteorological observing stations, so more based on precipitation. But I will give you a bit of an overview of what is in here and how this can be applied to satellite soil moisture remote sensing and drought and anomaly calculation. So there's a couple of steps that we need to take when we want to calculate the baseline. So what are normal conditions, and if we want to calculate the anomalies. So the first thing is that we need to prepare the data. So on the right side, you're seeing a time series of surface soil moisture for a point in Mozambique. This is from HSUF actually, and these are the daily observations. The first thing we need to do is mask for invalid values. So as I said before, we need to mask for example, areas where there is subsurface scattering, but also we need to apply the masks, like the flags that are available from the data providers. So this is the first thing that we always need to do if we do any calculations based on surface soil moisture data, but also on any other data set, basically from satellite observations, is always apply the quality flags that are provided within the dataset. Then the next thing is that usually for drought monitoring, we do not work with daily observations, but we work with 10 daily or monthly values. So the next step is to calculate monthly values. And the way that this can be done is there are different methods. So what we're seeing here in red are the monthly means, actually, based on the daily observations that we have in blue. The WMO guidelines tell us here that we can either calculate mean daily values, or we can do the highest or lowest values per month. We can also do the sum of daily values, or the numbers of days above or below a given threshold. So the sum of daily values is very much applicable, of course, for precipitation data, not so much for soil moisture data. So for soil moisture data, what's usually done is either the mean, so the monthly mean based on the daily values, or to take for drought monitoring, for example, also the lowest value could be taken. But here we're working now with the mean of the daily values for every month. The next step is then to calculate the normal or the long-term mean. So this can either be a moving window over a long period, or to calculate the average over multiple years. And so this means that for every January, for the years that you have your data, so in this case, this means that for every January until 2007 till 2022, you calculate, let's say, the average for January, and you do this for every month, and this is how you can get, let's say, the climatology or the seasonality, and this is what we see here in gray, right? So we see that this is always the same every year, this gray line, and in the background we can already see that the red line, which were the monthly means, that sometimes they are very much below the normal. So, for example, in 2012 we can see very low values. And we can also see that sometimes it's higher than usual, so much higher than the climatology or the normal. For example, in 2014, we have here very high values of soil moisture. So what do the WMO guidelines tell us? So there are three types of normals or averages. So the first one is the period average, which is an average of climatological data computed for any period of at least 10 years. Starting on the 1st of January of a year ending with the digit 1. So this would be, for example, from 2001 to 2011, etc., etc. What we can do here for this data set is that then we can actually calculate this for, let's say, 10 years of data. So we can have a period average of 10 years. A normal is the period for at least 3 consecutive 10-year periods, so at least 30 years of data. And then a climatological standard normal is, let's say, 1991 until 2020 or 81 until 2010. So basically, like most satellite data sets can only calculate period averages, and normals can only be calculated based on this ESA CCI data set that goes back until the end of the 70s. So this is also why this ESA CCI data set, this is the ESA Climate Change Initiative. This is really focused on getting long periods of data so that climate normals and climatological standards can actually be calculated. Okay, so once we have our climate normal or our long-term mean, we can actually calculate the anomalies. So the anomalies are, if we go back to this figure, the anomalies basically are the red line, which are the monthly means, minus the climatology, right? And so what we're left with then is that we have the anomaly, which is spread around 0. So anywhere where there's negative values, it means that soil moisture was lower than the normal, and everywhere where it's positive, it was higher than the normal. And then we can see here in 2012, indeed, that we have these very strong negative anomalies, actually. And then the next step is, how do we go from these anomalies to drought indicators? And as Professor Wagner also said in the last lecture, this is not that straightforward. So the first thing that you do is usually some sort of equation or conversion is applied to the anomalies. So here, for example, the anomalies have been, the z-scores of the anomalies have been calculated. And then also thresholds need to be indicated. So when is there a severe drought or a moderate drought or a mild drought? And this is not as straightforward as you would think, and this is what we'll go into as well now. But just very quickly, if you're using Python and you're interested in calculating anomalies and climate normals, you can also use the PyTestmode toolbox. So this is a Python toolbox for the evaluation of soil moisture observations, but also to calculate anomalies in climatology. So if you want to do a satellite validation yourself, you can also use this toolbox actually. Okay, so the next step, how do we go to drought indicators from satellite soil moisture? So there are basically two approaches for calculating drought indicators. The one is the approach based on anomalies. So this is based on deviations from the long-term mean, what we've been discussing previously. And these are indicators such as the Standardized Precipitation Temperature Index, soil moisture index, soil moisture deficit index, the soil moisture condition index, and the soil moisture anomaly percentage index. And their approach is based on plant available water. So these are based on salt properties in combination with soil moisture data. And the one here is the soil water deficit index. If you want to get an overview of all the different indicators that are available, what their advantages and disadvantages are, I would point you to a paper that's recently been published, which is Microremote Sensing for Agricultural Drought Monitoring, Recent Development and Challenges. So this is a literature review which reviews basically all these different indicators that can be calculated for satellite soil moisture. And I will go through a couple of them with you now. So first, some considerations. If you're using anomaly approaches, so based on deviations from the long-term mean, the advantage of this method is that it's purely data-driven. You don't need any other data, except you need a long-term data record so that you can calculate the anomalies, right? So what we were talking about before with the WMO guidelines is that you need at least 10 years of data to get a period normal or period average, but preferably a 30-year-long data record, of course. The other issue is also, or what you need to take into account, that how do you do with missing data, right? Because you need to calculate this average, this period average, and here you need to think about what to do with the missing data. The plant available water approaches, they do not need a long data record. And the other advantage is that they are directly related to the impact of drought on plants, because basically they give us an indication of how much water is really available for the plants to take up. The disadvantage is, of course, that you need ancillary data on soil properties to calculate this plant available water approaches. So this way you have, let's say, an additional uncertainty because you get this uncertainty also from your soil property data. And the other thing that you need to consider is that it's very important to think of the choice of drought indicator and its thresholds, because they really play a crucial role in determining drought severity and duration. And we're going to now look at the drought in Mozambique in the period 2015-2016. This drought affected 1.5 million people, mainly in the south and the central part. So we're looking here at precipitations from the UN drought report 2016. So we can already see that, let's say, the total rainfall was relatively low in the southern and central part of Mozambique. And you can see here very well that if you look at anomalies, you can see like there are very big anomalies in rainfall that, let's say, at some point in time there's 100 millimeters, or in some areas there's 100 to 200 millimeters less rainfall than there usually is. Also, if we look at the Standardized Precipitation and Evaporation Index, which is an index that is very often used for drought monitoring, which is based on precipitation data and also evaporation based on model data from temperature, we can see also that here in the central and southern areas of Mozambique, we have a very low SPEI, actually severe drought conditions. So this is also for February 2016, as was the rainfall data. Now, if we look at the different drought indicators, so this is the first drought indicator that we can calculate very easily from soil moisture. So here we're looking at quantiles of the anomalies. So basically, in which quantile of the whole data set does the anomaly fall? And then if it's lower than 1%, then it's the extreme drought. We have a severe drought, which is from 1 to 2%, etc., etc. And we can really see the drought develop right in Mozambique. So especially from December onwards, we can already see like a moderate to significant drought developing, which basically then ends in, let's say in February, we can see severe drought in a lot of areas in Mozambique. But also note that it's the similar spatial patterns, right? This was what we saw in the SPEI and the precipitation data. So like very severe droughts in the center and in the south of Mozambique. If we now look at the Z-score, so the Z-score is already a different indicator, which also has different classes of drought. So here we only have a severe, moderate, or mild drought. And what we can see is that actually where the whole period we're in a mild drought condition, which then develops into a moderate drought condition, and only in a few areas here we can see that there's a severe drought condition. So compared to the quantile method, the Z-score method actually shows us less severe drought conditions than this quantile method. If we look at the soil moisture anomaly percentage index, which was also a method based only on soil moisture, this is also classified into extreme, severe, moderate, mild, and no drought. And here we can actually see that the extreme and severe drought conditions are already occurring in October, and they only get worse throughout the growing season in Mozambique, where then in February you have quite a lot of areas with extreme droughts. So what we can see between these three different products is, or let's say it's the same soil moisture product, but these three different indicators, is that depending on the indicator that you choose and the thresholds that are set for these indicators, and these thresholds are based on the published literature. Based on these thresholds, we can get very different drought conditions. So this is really something to take into account, that depending on the method, you can get very different results, even though your data set is the same that you work with. So looking at, let's say, the three soil moisture-based drought indicators and comparing this to the SPEI, we can see very similar patterns, right? So let's say the most severe drought conditions are, let's say, in Maputo, Gaza, in Ambane, mainly, which we can also see here in the SPEI. So although the spatial patterns are similar, let's say the severity is very different. And we can also see that, for example, for the Z-scores, what we see is that there's no differentiation in drought severity in Gaza and in Ambane, which there actually is for the quantile method and also for the SMAPI method, the soil moisture anomaly percentage index. If we look at variations over time, so again, looking at these different methods, so what we're seeing here is a time series of the quantile methods. So you can see here the quantiles, and you can see basically the thresholds that there are for extreme, severe, strong, moderate, and mild drought. And you can see that the extreme drought is only for 2 months of the year. Over the whole time series, there are 2 months of extreme drought, 2 months of severe drought, and then 6 months of strong drought. This is logical, of course, because this is based on quantiles of the whole data set. So for every point, there will also always be 2 months of extreme drought somewhere. If we look at the Z-scores, what we can see is that there's only 1 month of severe drought, and then a lot of months where we actually have a moderate drought, and even more months where we have a mild drought. And then if we look at this soil moisture anomaly percentage index, we can actually see that we very often have an extreme drought with this method, 28 months actually over the whole record. A severe drought is for 19 months on top of that, and moderate drought for 21 months. So using the soil moisture anomaly percentage index, there would be actually a lot of months where we have an extreme drought condition. So the take-home messages of this are that you need to choose the right soil moisture data set for your application. So take into account the temporal coverage. So do you need a very long data record, or is also a short data record okay? You need to think about the spatial resolution. Are you looking at the whole continent, or are you looking at a very small catchment or agricultural site? And you also need to take into account the quality of the data set and where the data set works best. So you need to understand the strengths and weaknesses of the soil moisture product. So perform a quality check if you can through the QA4SM website, or you do this yourself if you also have, for example, in situ soil moisture data from your own meteorological service or from a farm or from your own sensors, and you can compare it to this to really see if it works for your area. And you also need to consider the physical limitations of satellite data. And this is for all data sets that are out there, also for precipitation, for NDVI, for anything. Always check, where does the data work, where doesn't it work? This is usually described in the user manual. But for satellite soil moisture, you need to consider dense vegetation, mountainous regions, and deserts where it doesn't work. The next take-home message is parameterization is extremely important for drought monitoring. So different indicators show wildly different results, right? So using a Z-score or using the soil moisture anomaly percentage index can give you extremely different results on soil moisture drought severity. So keep this in mind when you see a drought map or when you're calculating a drought map yourself. That it really depends on what your thresholds are that you choose and which parameterization you choose and which indicator you choose. Okay, and now we go to the case study. So this case study is over Senegal, and here I will show you what can be done with the drought indicators. So again, we have our drought that goes from a meteorological drought to an agricultural drought to a hydrological drought to a socioeconomic drought. And we'll be looking here, like, can we follow drought development through the water cycle from a meteorological drought, so precipitation, to an agricultural drought, where we're going to look at soil water deficiencies and also how this affects plants. So looking at the normalized difference vegetation index, the so-called NDVI, which is based on optical data, which gives us information on plant health. So we've been using here in this case study the CHIRPS data set for precipitation. So the climate hazards group infrared precipitation with station data in that data set. The soil moisture data set from HSUF, the root zone soil moisture from the Copernicus Global Land Service at 10 kilometers, and the Copernicus Global Land Service NDVI, so which gives us information on the vegetation states. If we look at these different data sets, so this is what it looks like. Here we see let's say the standardized anomalies for the June to August period for the rainfall, the soil moisture, the root zone soil moisture, and the NDVI. Just for you to get a feeling like what the data looks like and how many pixels we actually have at 12.5 kilometers over Senegal. So what we try to do is to track the rainfall deficits through the water cycle. So if we're thinking about drought and we think about how a drought develops, so the first thing that we're going to see is that we'll see a decrease or a deficit in the precipitation and the rainfall, which will be followed by a decrease in the surface soil moisture, the root zone soil moisture, and then vegetation. And this is what we've been trying also to track with our satellite data. So we were looking into if we can see a time lag between the precipitation data and the other data and the surface soil moisture data set and the vegetation. If we look at this, what we can see is that comparing, let's say, looking at time lags between NDVI, which is the vegetation data set, and the rainfall, the soil moisture, and the root zone soil moisture, we can see indeed that we have a time lag of, let's say, 1 month, more or less, between rainfall and NDVI. And then, let's say, this time lag becomes shorter between surface soil moisture and NDVI, where it's only 20 days. So, 2 to 3 weeks, basically. And then the shortest time lag or no time lag is seen between the root zone soil moisture and the vegetation data set. And this is basically what we would expect, right? So we see the biggest lag or shift between rainfall and NDVI and then soil moisture, and then root zone soil moisture. If we then look at the anomalies and also how they develop, so what we're seeing here is that on the top row, we can see precipitation anomalies based on the quantile method, as you're seeing here. So dark red means, let's say, extreme drought. We can see this on the top row for precipitation, then for surface soil moisture, the root zone soil moisture, and for the vegetation. What we can see is that the anomalies start basically for the precipitation, as we would expect, and they then actually develop into the soil moisture, the root zone soil moisture, and the NDVI. If we look a bit more in detail to the spatial patterns, what we can see is that, for example, we can see that the anomalies in the NDVI, so let's say the state of the vegetation, the most strong anomalies, so where the vegetation is suffering the most from drought, is actually in this northwestern area that we see here. But we cannot see this very well actually in the precipitation data. In the precipitation data, it also seems as if the southern areas are having a lot less precipitation. And actually in September, we can see that there is a surplus of precipitation. So there's more precipitation than usual. But what we can see is that in the soil moisture, and especially in the root zone soil moisture, we still see this shortage. So there's still this negative anomaly. So here we can really see that even though there's more precipitation than usual, it doesn't mean that the soil water is replenished and that there is actually still a drought that is continuing, which we can see very well in the surface soil moisture and the root zone soil moisture data. And also we can see that the vegetation is actually not recovering from the drought at all because of this higher precipitation than usual, but that we keep seeing these negative anomalies in the vegetation as well, which we also keep seeing in the surface soil moisture and the root zone soil moisture, but not at all anymore in the precipitation. Also, if we look, let's say we can also calculate, of course, the onset of a drought, the duration of a drought, and the severity of a drought. So here the onset of the drought is calculated based on in which decade, so which 10 daily period the drought started, and also the duration is calculated in decades. So a duration of 5 means 50 days of drought, basically. And what we can see, the onset starts in the precipitation, is then followed in the surface soil moisture, the root zone soil moisture is a bit later. Although the drought, or let's say the negative anomalies in the NDVI were already a little bit earlier, as you can see. But spatial patterns correspond much more to, let's say, the onsets of the surface soil moisture than it does to the precipitation. The same is also for the duration and the severity. So what we can see is that the duration and the severity in the precipitation are for the whole country very similar, right? For the soil moisture and the root zone soil moisture and the vegetation, we can see a little bit more variation, where the duration and severity were most strong in the northwest of Senegal for soil moisture and root zone soil moisture, and this is also in the vegetation. And what we can also see is that in the southeast, the vegetation actually has the shortest duration and severity in terms of drought impact, and we can also see this in the soil moisture data set, but we do not see this in the precipitation data set. We can also use the data for yield deficiency calculation, and this is an example here. So usually yield early warning is based on rainfall and NDVI data because rainfall is a driver of crop development, but the downside, of course, is that it excludes information on evaporation. And yeah, NDVI is an indicator of crop development. So the one is actually the driver and the other is the indicator. And so the idea is that soil moisture here is the missing link because it really links the plant available water to the plant. And so it's a more direct indicator of drought conditions than rainfall, for example, is. So what we did is, like what you can do, is to look at yield anomalies. So these are the standardized yield anomalies for Senegal based on the reported yield data per district. So this is, let's say, the average for all the districts, so country average of yield for millet over Senegal. This is the reported yield. And what we try to do is to use early season satellite data to model spatial and temporal variability in yield anomalies. And so millet in Senegal is planted or sown between June and August. So to say, mid-season is then August to September, and then it's harvested from September to November. And what we tried to do is that we tried to predict the yield at the end of the season already during the planting season, because if rainfall is delayed, it could be that the crops don't even germinate and they won't come up. So there is a possibility to do a yield prediction already in the planting season. And we did this with two input scenarios. We use satellite-based rainfall data and NDVI, and we use satellite-based soil moisture data and NDVI. So we use chirps and NDVI and the HSAF soil moisture and NDVI. What we first did is we tried to look at how much of variability in the yield can be explained by the different data sets. If we looked at the at the planting season, we could see that rainfall could predict almost 40% of the variability in the yield, and soil moisture a bit over 40% of the variability in yield, whereas the root zone soil moisture and the NDVI were below 20% that they could explain from the yield variability. If we looked mid-season, so August, September, we could see that rainfall was less important for predicting yield variability, but that soil moisture, soil water index were very important for predicting yield variability. So predicting basically deficiencies in yield, and that the NDVI was still the lowest to predict any yields for millet in Senegal. Now, if we combine the data sets and try to do a prediction, what we can see is that if we combine chirps rainfall and the NDVI to do a yield prediction, we capture some variability, but not all. And specifically, in Senegal, there were severe droughts in 2011 and 2014 and 2016 to some extent. And we can see that with the rainfall and NDVI, we really do not capture these deficiencies, let's say, in the yield. So these negative yield anomalies are not captured with this method. Whereas if we replace the rainfall data with the soil moisture data, what we can see is that we much better capture these drought events, let's say in 2011 and 2014, but not in 2016. So what we can then do also is that we made this model and we can change, let's say we can trade space, the time for space. And so we can use this model that we made for Senegal. And because our data is of course available for every pixel, in this case, we did it every 10 kilometers, we can actually calculate the yields for millet or the yield deficiencies for millet for every year on a spatial scale. And this is what we're actually seeing here. So this prediction is done in July. And let's say the harvest of millet is from October onwards, right? So why is this important to do? So what we're seeing here is this yield deficiency prediction based on chirps, rainfall data, and NDVI for 2019. And what we see here on the right is a map of the water requirement satisfaction indicator from African Risk View. And this is the end of season report for 2019. And this is the data that is used by the African Risk Capacity to do payouts for drought insurance, basically. And what we can see here is that we don't really capture this drought conditions that are seen here in the western area of Senegal. We don't really see this in the rainfall and NDVI prediction. But if we're using soil moisture instead of rainfall data, what we can see is that we get a much better prediction of these drought conditions, right? We really capture these drought conditions and this yield deficiency in the western part of Senegal, which we didn't actually capture using precipitation data. Now you think, why is this important? Because we have the water requirement satisfaction indicator already, so why would we need another indicator? The thing is, this water requirement satisfaction indicator is at the end of the season, and our prediction was already made in July. So we can already have a very early indication of where the harvest might fail or where the crops have failed, so that you can already take early action So you have an early warning, so you can take early action and already prepare for any, let's say, you can mitigate the drought effects, basically. So this is why this method is very interesting to use, and also the use of soil moisture data is very interesting because it can give us a much earlier warning for drought conditions and yield deficiencies. So the benefits of using satellite soil moisture for drought monitoring is it's complementary to existing products such as precipitation and NDVI. It provides us continuous monitoring from satellites. We can better capture drought because we can track it from precipitation to soil moisture to vegetation as well. And we can improve our yield predictions as well by using soil moisture data. So thank you very much for your attention. And I think now it's time for any questions that there are. Okay, let's see. So we have 3 questions from Mahfouz and Maya. So first is, let's say, how deep in the soil do active sensors penetrate to derive soil moisture, 10 centimeters, and if the depth varies with the spatial resolution of the sensors. So yeah, indeed, let's say the penetration depth really depends on the frequency of the satellite. And so let's say the frequencies that are currently used for satellite soil moisture are mainly L-band and C-band. So these are 1.4 and 5 gigahertz, where L-band sensors penetrate a bit deeper. So L-band sensors penetrate, let's say, around 10 centimeters, and C-band sensors would penetrate, let's say, 2 to 5 centimeters, something like this. And the next question is what software we use to access and process soil moisture data. So we use actually Python for everything. And also the packages, like the Python packages that we use in the code, is freely available through GitHub. So what I showed you before, the PyTesmo package, which is available on GitHub, is also developed by us. And there's also on our GitHub, there's a lot of data available. Then the next question is, in Mozambique, how do forest areas affect the anomalies that we use? Yeah, indeed, forest areas affect the anomalies, but only if it's a very dense forest. Actually, so in this case, not as much. Yeah, because we're mainly looking at agricultural areas in Mozambique. So, and also the forests aren't as dense in Mozambique that we really have problems with it. The problems are mainly in, let's say, the Amazon, Congo, etc. So really tropical rainforests. Yeah, so the next question is there any way of using L-band passive microsatellite soil moisture SMOS for drought monitoring? Yes. Definitely, we don't have to wait for 2 decades to have a longer record of soil moisture. The one option that you can do is that you calculate drought indicators based on plant available water, right? So that you would need, for example, wilting point and field capacity, and then you can really calculate drought indicators from SMOS as well. Another thing that people have been doing, which is also quite interesting, is that to calculate the climatology that is based on a long-term data record, what they did is they calculate the climatology based on model data and then scaled this to the SMOS data and then use this as the climatology and then do the anomalies based on the SMOS data. So this is also a possibility, but it does, well, in my opinion, brings in a little bit more uncertainty because then your climate normal is based on a different data set than actually your anomaly calculations are. Yeah. Is there a difference between using NDVI anomalies or vegetation condition index, which uses max min values rather than mean and standard deviation? Yeah, yes, there is. And so in this case study, we used NDVI anomalies. But of course, you can also use the vegetation condition index, and actually one of the combined drought indicators actually uses the let's say soil moisture condition index, temperature condition index, and vegetation condition index, indeed then scales them all between maximum values. The difference between using maximum scalings like the VCI and mean standard deviation is that maximum methods are much more sensitive to outliers in the data than the mean and standard deviation method. Okay, next question. So from Peter, how can you differentiate soil moisture from undisturbed soil structure from disturbed agricultural soil structure? Yeah, so this is one of the things that in most soil moisture retrieval methods is not taken into account. And so actually, if we think about that, let's say the soil roughness, but also the soil characteristics are usually not taken into account in the soil moisture retrieval algorithms. And so what we think usually of surface roughness, as we would like the management practices change the surface roughness, right? There's a difference between a tilled soil and a plowed soil, for example. This is not taken into account because we assume the surface roughness is stable over time. So this is one of the challenges that we currently have in satellite soil moisture retrievals, especially if you go to very high resolution data, because then you can really have data over one specific field. And so your one pixel is a field that's plowed, the other pixel is a field that's not been plowed or is barren, so to say. And then we can see a difference in the backscatter, or let's say in the brightness temperature, so the satellite signal, which is most likely coming actually from the differences in soil structure and not as much from surface soil moisture. So yeah, this is definitely a topic that we're still working on. So next question is, did you compare soil moisture from SMAP with chirps and how to check its validity? We haven't done this because SMAP, we haven't used SMAP because it isn't available for a very long time. So it's now only available for 7 years, which is relatively short. Like as the WMO states, like to get a period normal or period average, you need at least 10 years of data. So we haven't looked into SMAP data, but I have to say that SMAP soil moisture is actually very good. It performs very, very well globally. I think it's one of the best soil moisture data sets that is available, but unfortunately it's not such a long data record. But SMAP soil moisture is used very often to do this plant available water methods. So really scale it with field capacity and wilting point and then calculate drought indicators. So this here SMAP is a really good data set. If I can mention the GitHub link, yeah, I will post it in the chat afterwards. Next question is, do you have any idea about other remote sensing products such as GRACE, and how can GRACE data be utilized for soil moisture extraction? And is this method useful for accurately measuring soil moisture levels? So actually GRACE provides us information of the total water equivalent. So this gives us information on the amount of water that's in the groundwater, the soil, and the vegetation. So it's relatively difficult to use it to measure soil moisture levels, but it does give us a general indication of the water availability, let's say, on the Earth's surface. And so what GRACE, for example, is used for in studies is to see how much extraction there is of groundwater for irrigation. This has been done by combining different satellites on different satellite products in combination with GRACE. Also, recently there has been a very big project by ESA, which used GRACE data in combination with precipitation data, satellite soil moisture data, evaporation data, to try and close the water cycle, basically. So really, like, how much water is there available everywhere, and can we then split this up in the different components? But this is a relatively new field of study, so the results of this are relatively new. But if you're interested in this, I would say take a look at the G3P project results. So I'm typing this there. Okay. Yeah, so a good question. How does one select the right indicator thresholds? Are there specific thresholds for specific regions? Yeah, this is the thing that we're working on now as well. So this is it's still a relatively new field of study to use satellite soil moisture data for drought indicators, and specifically also to try and use them, for example, in drought risk insurance. And so the World Bank and also Austrian Development Agency, for example, are very interested in particularly this. So how can we set these thresholds to use satellite soil moisture? So this is really something the community needs to work on. Okay. Then next question is, what is the relationship between stream flow and drought? Can we use stream flow as an indicator? Yeah, so there's definitely a very strong relationship between stream flow and drought. And there have been a lot of studies also looking into this. And indeed, we can use stream flow as an indicator, but stream flow is an indicator of an hydrological drought, and of course. Yeah, next question is, can we use the baseline from one satellite product and the real-time data from another, knowing that there may be a difference in methodology to calculate each of them? Yeah, this is a very good question, and indeed you can do this. You can also do this with, for example, model data and then use the real-time data from a satellite. So this is definitely possible, and there have also been quite some studies that have been doing this specifically. So yes, this is definitely a possibility. The way to do it is that you scale different data sets to each other. So you do, for example, a mean standard deviation scaling between the long-term data record that you have to the satellite near real-time data that you have, and then calculate the, let's say, the normal, the baseline from that, so that they match to each other. Then the next question from Daniela is it okay to use soil moisture data in mountainous areas? Yeah, this is tricky because mountainous areas are relatively difficult because, first of all, soil moisture retrieval from satellite doesn't work if there is snow cover or frozen soils, which is very often the case in mountainous areas. So usually in these regions it doesn't work very well, and so you should be really careful using that you should really provide or use the data that is provided on the quality for the different products, because usually they have a flag or a mask that you can apply to take out these observations that were done under snow and frozen soil observations. And then how do you handle missing values? Yeah, missing values are relatively problematic, I would say. The advantage with satellite data is that usually you have observations every other day. It's not as problematic that if a sensor, it's not like an in situ sensor that when it's broken that you need a couple of weeks to fix it. Usually it's relatively continuous. And the advantage for agricultural drought monitoring is that in this period there usually isn't any snow or frozen soil, so you actually have the data. So for satellite soil moisture, it's actually relatively okay to do. If you calculate monthly values, you usually don't need to do anything about the missing values. Okay, do you have any methodology for extracting soil moisture data for a small administrative area? So if you have a very small area, I recommend that you use Sentinel-1 data, which is at 500 meter sampling. And this is also available through the Copernicus Global Land Service. But unfortunately, only for Europe. So I will quickly provide you the link for this one. So that would be this one. The next question is, can this approach be applied to the monitoring of temporary wetlands in an arid environment? Yeah, yes, it can. Well, let's say remote sensing, satellite soil moisture can generally be used for this. It is, although, a very different method, because as soon as you have open water or wetlands, the backscatter signal gets very different. This was what was discussed by Professor Wagner in the last lecture, is that you can use satellite backscatter data from Sentinel-1 for monitoring floods. And this is the same as you would do for temporary wetlands. So yes, you can do this. But let's say it's not as much related to the soil moisture retrieval, but it's more related to the backscatter by itself, because satellite soil moisture retrievals also fail if there's open water, because as soon as you have a water surface, the backscattering mechanism changes very much. So basically the surface is like a mirror, and you get extremely low backscatter values. So yeah, take this into account, that the satellite soil moisture retrievals will probably be wrong, but you can actually use this in a different approach, also monitor open water. Then the next question: in your studies, do you consider irrigation, as this would alter results but not really reflect drought conditions? And if we use auxiliary data for irrigated areas? Yeah, so the thing is that, so this is actually the nice thing about our method of using soil moisture, because the satellite soil moisture is including irrigation data, and this is an advantage compared to precipitation, and also compared to using models, because if you only look at precipitation and temperature data, you're actually not taking into account irrigation. But of course, satellite soil moisture data is sensitive to irrigation, so this actually includes the irrigation signal. Indeed, it would alter the results in a way that there are no drought conditions based on the soil moisture drought indicator, even though there are drought conditions, but these are mitigated by irrigation, for example. So this is really then depending on the application that you have, right? Do you really want to see how many crops are failing, or is there a yield deficiency? Or do you really want to see, like, in which area do I have drought conditions? So yeah, this is a bit of a trade-off. And in a way, you can use the combination of having model-based or precipitation-based drought indicators and soil moisture-based drought indicators to actually see these areas where there is irrigation and where there isn't irrigation. And so these are also, there's quite a lot of projects from ESA as well that look into using satellite soil moisture data to identify areas where there is actually irrigation. And so this, there's recently a very nice paper which does irrigation mapping at extremely high resolution, which is actually quite nice. Let me just quickly look it up for you. Yeah, so that would be that one. Can we get the GitHub link and today's slides? Yes, definitely. Yeah, I'm not sure how the slides are being distributed, but I can definitely make them available, and maybe Job can say something about that. I'm not sure. And as for the GitHub link, I will post it in the chat. So yeah, so so this is the link to the, I hope you can see the answers. That's the GitHub link. So yeah. Okay. I think all the I think everything has been answered so far. Are there any other questions from people? Okay, if not, then I leave it at this. Okay, then have a nice afternoon and good luck on the rest of the series.